So last time we talked about explicit methods. Today we're going to talk about implicit methods, or specifically the most popular choice of implicit methods for elasticity problems is the Newmark Beta family of methods, okay? So Newmark Beta, and you'll see where the Newmark's a guy's name, right? And Beta, you'll see where that comes from. So in this method, we have u at n plus 1 equal to utility n plus 1 plus beta delta t squared is acceleration at n plus 1. And utility n plus 1 is equal to un like that. And v at n plus 1 is v tilde n plus 1 plus gamma delta t So what the Newmark Beta is sort of an interpolation. I mean, it's sort of an interpolation between a fully explicit method, fully Euler explicit method, and a fully Euler implicit method. Okay, and so the beta term is the sort of interpolant between the two methods. It gives you a higher order in time, and the gamma is a damping term on the velocities. Okay. So beta is some parameter of the solver, and gamma is some damping parameter. And so then when we would solve for the new accelerations, like that, for beta positive, obviously. And so a couple special cases of this, if we choose beta equal to 0 and gamma equal to half, we have an explicit central difference scheme. That's what we derived last time. If we choose beta equal to a half, gamma equal to a half, we have an undamped trapezoid rule. Right, so trapezoid rule, remember, if you have some function over time, in a trapezoid rule, you decompose time into little trapezoids, right? Do what? Central difference, that's an explicit scheme that we derived last time, actually. It works out to identically the same formulation that we derived last time. So gamma should be greater than a half, and it provides a damped response on the velocities that's proportional to gamma minus a half. And so these methods are, for linear problems, unconditionally stable for beta greater than or equal to gamma over 2 greater than or equal to 1/4. And so what we'll do with these problems is we're going to define a residual one over beta t squared. And with this residual, we'll use this to construct what's called a tangent stiffness matrix. And it is the gradient of the residual with respect to u. So really, I should say this is ui uj, so it's a gradient, or ri uj. And that's equal to beta delta t. So remember, our force internal was like our stiffness matrix, which was, for elasticity problem, that's the integral over the domain B transpose CB HE, if it's 2D, HE dA essentially, right? So the internal force Kij Uj, right? So then if we take the derivative of it, we have partial Kij partial Uj plus partial plus Kij partial Uj let's see, I should probably use a different should probably use a K here, right? K. Partial UK. Well, if it's a linear problem, right? This first partial Kij partial UK, this is 0, right? I mean, it's a linear problem. So because there's no u's in this thing. Right? So this would be 0, and then the last term would be Kij delta JK, which is equal to KIK, right? So, in other words, that's just a long-winded mathematical way of saying, for a linear problem, that last term, partial F internal partial uj is just a stiffness matrix. Right. Yeah.
The second one, if 1 over beta delta t squared, does it have m delta ij or something?
There should be an m there, actually.
Is delta ij as well?
Yeah. Well, no, mij. Yeah. Sorry, left out a term. Huh? No, it's no. This is this is not like a quasi-static or a dynamic relaxation. This is actually an implicit method. Right? So you'll have the dynamics of the accelerations in there, albeit at a lower frequency because of the damping. So, but the reason I wrote it real general like this is because this is the method we're going to use to solve basically plasticity problems, okay? And in a plasticity problem, this is not valid anymore. And in a plasticity problem, we would write this, right? Because remember, CB is the stress. Oh, I'm sorry. CBU is the stress. Okay. So this is not strictly K, but rather K that's a function of U. So in this case, when we do that partial derivative operation, we actually, we actually, that partial K partial U is not, there's something there, right? It's a non-zero term. It turns out we won't actually, you don't actually construct a stiffness matrix in that scenario. In the sense that, you actually just compute the partial of F internal partial Uj. Because the this is actually F internal. Yeah, I'll give you some ideas about how to do it. We'll talk about nonlinear problems next time. But the critical thing is that it turns out that when you do, we're going to use Newton's method to solve a nonlinear problem, right? And with Newton's method, you have a quadratic convergence, right? Every time the residual should be cut in half, essentially, every time, every step you take, okay? But to maintain that quadratic convergence, remember in your F internal, because in your stress, you have a return algorithm. You have some numerical procedure. You're off the yield surface, you got to get yourself back on it, right? So you have some return algorithm, some numerical procedure to get yourself back on the yield surface. And it turns out when you take that derivative up there, it has to be consistent with the return algorithm. So what we call that tangent stiffness over there is, we call it the consistent tangent stiffness matrix. And that means it's consistent with the return algorithm. And we have to have a consistent tangent stiffness to maintain a quadratic convergence of the Newton iteration. So what we'll do, and one way you can guarantee that is through finite differencing, but it's slow. A better way, if you're a C++ programmer, as Michael will tell you, he wrote a whole paper on this, is to use automatic differentiation scheme. So automatic differentiation is sort of a computer implementation of the chain rule, and you can use some of the C++ magic to string it all together. And the cool thing is you get analytically exact derivatives. There's no approximation. I mean, there are two machine precision exact derivatives, as if you would have figured out what it is yourself by hand, but the computer takes care of it for you. And it's just as fast or faster in some cases than finite differencing, so it's more accurate. The other way is to actually figure out what that is by hand, which means you have to basically compute all those chain rule derivatives through the whole stress integration algorithm, which can be non-trivial if you have a complex plasticity model. So then we'll make a flow chart for implicit. Initialize your velocities, displacements, stress, step equals 0, time equals 0. Let's see, compute so then we're going to estimate the new displacements with either the old displacements or those old interpolated displacements, the utilities. And then Newton iterate. And I'm going to write down this procedure here, but we're going to talk more about it next time. So in the Newton iteration, we're going to compute actually this and this and this should be just capital F O, where F is equal to the force internal plus the force external. So then we have a residual, find the tangent stiffness matrix. Modify the tangent stiffness matrix for the boundary conditions. These are, for our essential boundary conditions, this is the same procedure. We're going to put ones on the diagonal, right, and zeros elsewhere. We're going to solve for the displacement increment. And check convergence of our Newton iteration. And so you can have whatever convergence criteria could be anything. It could be, the change in displacements from the old to the new. It could be the magnitude of the residual. I mean, ultimately you're trying to drive the residual to zero. So you could have the magnitude of the norm of the residual, or you could check both and have criterions on both of them. And you could have other criterion too. So now I'm going to go back over here. Step 6 will be to update the displacements. And step 7, if you want, just like before, to check the energy balance. So that's the implicit method or Newmark Beta method for elasticity problems or elastoplastic problems.